Welcome, everyone, to this afternoon's research seminar, a16z Crypto. Very pleased to welcome Yannai Gonczarowski. Yannai has had more distinct chapters in his career so far than most of us, I would say. He had a chapter as a professionally trained opera singer. Talked to him about that. He had a chapter as a computer scientist, indeed as one of the really most visible superstars of the econ CS area for the past decade. And now he's in a chapter as an economist, as a faculty member at Harvard in both the econ and CS departments. Today he'll talk about something very near and dear to my heart, quantifying inefficiency.
Thank you so much for this introduction. I'm not sure it's completely earned, but thank you. So this joint work with Ella Segev, who's a wonderful game theorist at the Hebrew University. And I'm going to start with two slides that I'm going to ask the economists here to ignore, but this is more kind of, making sure we start at the same level. So let's talk about utilities for a second. So it took me quite a while to realize that computer scientists and economists actually mean two different things when they say utilities. Usually, giving a bit of a oversimplification of both, within computer science, especially within the computational social choice community, they think about utilities as giving additional intensity information beyond the ordinal preferences. While in economics, at least for the last 65 plus years, utilities are no more than a representation of the ordinal preferences. So you might ask, what do these numbers mean? So these numbers do not reflect intensity, they reflect risk attitudes. As an example, if my utility for alternative A is 8 and for alternative B is 4, it does not mean I like alternative 8 twice as much as alternative 4. It rather means that if my utility for a third alternative C is 0, then I'm indifferent between getting B, this 4, for sure, and a 50-50 lottery between A, whose utility is 8, and C, whose utility is 0, because the expected utility here is 4, so I'm indifferent between this 4 and that 4. Accordingly, if my utility for A, instead of 8, were 5, it doesn't mean that I would have liked A any less. It would still be my most preferred alternative. It would just mean that this 50-50 lottery between A and C, instead of giving me expected utility 4, it would have given me expected utility 2.5, meaning that I would have strictly preferred B over this lottery. So in economics, we think about these numerical values as reflecting risk attitudes rather than, so this means that I would have been more risk averse. I would have preferred the sure thing rather than the lottery. So utilities, these numbers, are actually a concise representation of preferences over lotteries. Via expectations, we have a number for each pure alternative, and we evaluate a lottery by taking the expected utility and comparing to the expected utilities of other lotteries. And you might wonder, when preferences have such a nice, concise representation, the answer is any von Neumann-Morgenstern preferences have such representation. What are these? There are 4 fairly standard, agreed upon in the sense that most preferences would satisfy these axioms, such that if a preference satisfies these 4 axioms, then we call it a von Neumann-Morgenstern preference, and it has this nice representation. In particular, this representation is only unique up to an affine transformation. If you multiply all utility values by 5, or you add 13 to all utility values, all of these comparisons would remain exactly the same. And this gives the next thing, which is a bit of a thorn, that utility numbers, cardinal utilities, are not interpersonally comparable. If we multiply, we can multiply my utilities by 13, but not multiply Tim's utilities by anything. Either before the multiplication they were not comparable, or after they weren't, but actually they never were. There is no way to compare my 5 to Tim's 5, which also means that it is not particularly meaningful to sum these two 5s up together. To give you one example, if you open Wikipedia under price of anarchy, the first example is of calculation of the price of anarchy. So what do they say? This is a prisoner's dilemma. Defect gives total disutility 10. Cooperate gives total disutility 2. They do the ratio, they see it's 5, and they say the price of anarchy of this game is 5. What's the problem? If you add 1 to all these utilities, you're allowed, they're only unique up to an affine transformation, then you need to take the ratio between 4 and 12, which gives you a price of anarchy of 3. If you subtract 1 from all these utilities, you need to take the ratio of 0 and 8, gives you a price of anarchy of infinity. Price of anarchy is the ratio between the equilibrium, here sum of utilities, and the first best. And this raises the question of, is the price of anarchy here high? Is it low? How do we compare this to other games? Or more generally, what do we learn from these numbers except that the equilibrium is not efficient? And since I'm now speaking to computer scientists, I'm allowed to add this slide that I usually don't add. Is it high? Is it low? Same text, yeah.
Is that literally the first example on the Wikipedia page?
This is literally the first example on the Wikipedia page, yeah. So I should note this is not a general criticism of the concept of price of anarchy. If you read Tim's paper, you will see that he is very careful. He never talks about the sum of utilities. He talks about a cost function that is exogenously given, and that is the thing that he takes the ratios of. I wish everyone were as careful as Tim. So let's...
I mean, just for history, like when I was first doing the price of anarchy work, 2/3 of economists told me some version of your first slide.
Yeah, so that's...
So like, you're not making up the story.
No. This really is the thing that gives the knee-jerk reaction to economists when they see these results. So today, this is not going to be about Web3, I apologize, but since we have so many wonderful interns here who are truly making a commendable effort to talk across discipline boundaries, this is, at the very least, an example of the lengths that I encourage you to go to talk across these boundaries. Okay, so really beginning of talk is now. So social choice theory exists since, I don't know, centuries, and it usually asks how to aggregate the ordinal over lotteries, if you wish, preferences of individuals over alternatives. It usually asks questions such as, is alternative A societally preferred to alternative B? Is alternative A societally efficient, meaning societally most preferred among all alternatives? It falls short from generally answering questions such as, by how much is alternative A societally preferred to alternative B? Or how societally inefficient is alternative B? Is it very inefficient? Is it 99% efficient? There's something that's just a little bit more, but really it's very good. So these questions are neither attempted to be answered nor answered. And what I'm going to do today, I'm going to axiomatically define a cardinal measure of inefficiency of alternatives that's going to allow us to ask these questions. It's going to be cardinal. It's going to be comparable across settings, think across different games, and it's going to be cardinally unique, and yet it's going to be based solely on the ordinal over lotteries for Neumann-Morgenstern preferences rather than the utility values. Why do this? Because I like what I call inefficiency bounding theorems, and computer scientists call approximation theorems. These are, I think, an early major contribution of computer science to economics. These are not theorems that say this equilibrium or this mechanism is efficient. These are theorems that say this equilibrium or mechanism is quantifiably not far from efficient. Computer scientists call it the price of anarchy, because at some point computer scientists realized that the input to their algorithms might be affected by incentives, and they were like, oh, this is anarchy. So you can like the name, you can not like the name, but that's the name. Example number 1 of an inefficiency bounding theorem. This is my first example even when Tim is not in the audience. This is a very rightfully celebrated paper from 2002 that says the cumulative driving time in every equilibrium of a large class of congestion games. There are many cars, each has an origin, destination. When they drive the same road, they make each other slower, etc. The cumulative driving time in equilibrium is no greater than 4/3 the optimal cumulative driving time. So it means that if you could direct every single car to minimize to minimize the cumulative driving time. If you could get it down to an hour, it means that in equilibrium, it's not going to be worse than an hour and 20 minutes. This is interesting. It should be compared to the more classic approach of characterizing when equilibria are inefficient or that they might be inefficient or something like that. So this is one example. Second example is a much newer one that I also really like, saying that, okay, so the setting is a first price auction. We have independent bidders' values, and we're looking at a Bayes-Nash equilibrium. Since different bidders' values are drawn from different distributions, the equilibrium need not be efficient. But turns out that if you take the expected welfare, meaning the expected value of the winner, then it is no less than, at equilibrium you do this, then it is no less than 86% of the expected optimal welfare, meaning the expected highest value. And this is regardless of the distributions that you sample from. So again, a very insightful inefficiency bounding theorem. I should say, 86% really is a way of saying 1 minus 1 over e squared. And the reason I mentioned this is tight. There are actually settings, meaning distributions for the bidders that give you 86% and no more. And I also like this example because it shows you the power of inefficiency bounding theorems not only in what they tell us, but in the rapid development that they allow between papers. This started with a paper that showed 63% more than about a decade before this final result was published. Then it was gradually tightened over the years with more and more papers until they got to 86%. And compare this to the standard in economics, which is you sit on this until you get the optimum. If it takes you 10 years, it takes you 10 years. This allows for much more rapid development. When your ideas stop, someone else's ideas can start. So we have two examples. Each of them has what you might call a social inefficiency measure. One of them is the driving time. The other one is the expected welfare. That's a social efficiency measure. And there are three properties that make these interpretable in an economic sense. One of them is that they aggregate ordinally over the individuals in a way that makes sense. They use minutes to sum up over different individuals, or they use dollars to sum up over different individuals. And this is, of course, much more challenging if you don't have interpersonal comparability. This is the usual problem that has plagued social choice for more time than any of us were alive. But there are two more problems that don't usually crop up in social choice. The first one is what we call intra-context cardinal comparability. This is the property that for each of these things, 90% is twice the inefficiency loss of 95%. This is something that is challenging to do if you don't have a common unit of measure. One example you can think about is the Nash social welfare function. If you're familiar with that, it's a well-studied social welfare function in economics going back to the 70s and before that to the 50s. You take the product of everyone's utilities, normalized so some kind of worst case is zero, and there are beautiful papers that show that the order induced by this has wondrous properties. All of these papers give axioms that show you that the order induced by this is a good order. I'm not familiar with any paper that justifies the specific numerical values, meaning that if you apply any monotone transformation to the Nash social welfare, you take 2 to the power of that, you take the log of that, you take the tangent of that, you get something that is as justified by all of the papers, at least that I know, that justify the Nash social welfare. Meaning that they're talking about 90% versus 95% of the optimal Nash social welfare is much harder to interpret, is much harder to compare. So this is intra-context cardinal comparability. And here I can go back to a very classic book in economics from 1957, Luce and Rifa, and they tell us one must develop an almost inhuman self-control not to read into these numbers those properties which numbers usually enjoy. For example, one must keep in mind that it is meaningless to add two together or to compare magnitude of difference between them. If they are used as indices that represent an order over certain alternatives, the only meaningful numerical property is order. 1957. Next comes inter-context cardinal comparability, meaning the ability to compare across different games. So for example, here when we say 120% of the optimal driving time, or 133% actually the optimal driving time, this carries similar meaning across similar games because there is a natural reference point here. This essentially says in every congestion game, if you take instantaneous arrival as 0, and you take the optimal cumulative driving time, and you take the difference between these two, and then you take the difference between instantaneous arrival and equilibrium, the latter is no more than 4/3 of the former. And it is this reference point that gives meaning to this measure. The same here. In the auction setting, what we implicitly did was normalize no trade to 0. And then we asked, if you take the distance between equilibrium efficiency and no trade versus optimal efficiency and no trade, what the ratio is. And this is the thing that gives meaning to saying 86% across games. So this is another challenge that one would have to contend with if they would want to define this in a general way. And I should note here, again from Luce and Reifa, they say the non-uniqueness of the 0 point is of no real concern in any of the applications of utility theory, but the arbitrary unit of measure gives trouble. And I will add here that in our setting, and more generally for any approximation theorem, the non-uniqueness of the 0 point is of a real concern as well. If you shift everything by 5, the optimum remains optimum. The ratio between optimum and something else goes crazy. So today, the goal is to define machinery to allow us to give meaningful inefficiency bounding theorems in settings when we don't have a reference point, we don't have a common unit of measure, we don't have interpersonal comparability. Model. So a context is a pair. X is a finite set of alternatives, and then we have n individuals, and each of them has von Neumann-Morgenstern preferences over lotteries over X. You can think about this as the set of outcomes of a mechanism, or the set of strategy profiles in a game, or whatever. A social inefficiency function specifies a non-negative number, we're going to call that number an inefficiency, for every pair of context and specific randomized alternative, meaning lottery over alternatives in this context. So we can ask in this context, this specific lottery over alternatives, what's the inefficiency of this? I should note before the mathematicians in the audience object, I know this is not a function technically, there is no set of all contexts, therefore this is not a function, technically it's a family of functions, but nothing that I'm going to do today is going to give any set theoretical issues. So I'm going to call this a function and we're going to be fine with that. So in this paper, we axiomatically define a unique social inefficiency function. It's going to be unique up to a single multiplicative factor across all contexts, meaning that if you multiply it by 5 in one context, you need to multiply it by 5 in all contexts, which means that you can still compare numbers across contexts. This is going to give meaning to statements like, you take your favorite mechanism, you calculate its worst case inefficiency across a broad family of contexts, and then you say, no other mechanism can improve upon this worst case inefficiency by more than 28%, for example. And we're actually going to prove this precise theorem as our application. We're going to use techniques from computer science to prove that random serial dictatorship, very popular matching mechanism, is approximately optimal among all truthful ordinal matching mechanism. So no other mechanism will be able to shave more than 28% off the inefficiency of random serial dictatorship. That's going to be our application later.
So quick question. So
Yeah.
it's not like linear in the probabilities, right? So the function, so it takes as input like a distribution
I'm not
over-
saying what it is yet. It takes as input a context and a randomized alternative and gives you a number. Could be linear, could be not linear, could be whatever.
I shouldn't necessarily think of it as linear, is what I'm
Yeah,
saying.
you
Right? As
shouldn't.
opposed to saying context, comma, alternative, with that extended to lotteries through expectation.
You're right.
Okay.
I'm gonna tell you a secret, it's gonna be linear,
Oh, okay.
but we'll get there. So one thing that you might notice, which is a cousin of Tim's question, is that the inefficiency is not only of the alternative, it's of the alternative within the context. The context matters, which means that everyone's preferences over all alternatives, not only this one, matter. So again, here we can go back to 1963. This is the second edition of Arrow's influential book, and he tells us that Guibault, I'm not citing Guibault because Guibault is in French, so I'm telling you what Arrow said in English about Guibault. So Guibault argues that a social welfare function based on individual utilities which are meaningful only up to monotonic transformations must be what is mathematically termed a functional, not a function in the ordinary sense. That is, each social choice must depend on the entire individual ordering. This, in a sense, has already foreshadowed or foreseen that you would need also all of the other preferences here when you talk about a specific alternative. So we have a social inefficiency function, gives us a non-negative number. We call it the inefficiency. Lower inefficiency is better. Perhaps the most controversial thing I'm going to say today is that we allow for this inefficiency to be infinite for some context, comma, alternative pairs. Technically, it makes life much harder for us, so this is not a shortcut. Conceptually, I'm going to now claim that it's required to satisfy two properties that we think are mild. First one is Pareto monotonicity. This is going to be one of our axioms. It says if we have fixed some context, we have alternative A, alternative B. If everyone prefers A to B, then the inefficiency of A better be lower than that of B. If someone even strictly prefers A to B, then the inefficiency of A better be strictly lower. That is Pareto monotonicity. The other property, this is more of a mouthful, is what we call invariance to dominated alternatives. So what's going on here? We're going to say that a social inefficiency function I satisfies IDA, invariance to dominated alternatives, if whenever you take a context, and now you throw out of this context some weakly dominated alternatives. So everything that you throw out is weakly dominated by some lottery over stuff that you keep in. And then you take a look at some alternative that's a lottery over the stuff that remained. Its inefficiency in the original context and the context with stuff thrown out should be the same. The way to think about this is that usually our models model the things that we really have a trade-off between, the things that we might be interested in. They don't model points that say, well, the world might explode completely, or, everyone might, incur some real serious issues or whatever. So we don't want the inclusion or non-inclusion of such points to change our analysis. This is similar to the price of anarchy, which takes a look at the cost or gain at equilibrium and at the optimum, and not at other suboptimal inefficient points. So this is not one of our axioms. It's a desirable property that's going to be implied by them, but we think it's a property that you would want to satisfy to not depend on the choice of modeling to include irrelevant points. And I'm now going to prove to you, this is going to be the only proof we're going to see today, that these two together imply that you must allow for infinite inefficiency. I should note, we can skip this, but Arrow has already, back in 1951, criticized a specific social choice function that normalizes each utility to the function to the range of 0, 1, and then added them up, that the order induced by this is sensitive to the addition or removal of alternatives that are dominated by all other alternatives. And arrow says this is extremely unsatisfactory. So this is kind of an ordinal version of our IDA, but again, the idea that this is undesirable goes way back. Okay, so here's the context.
So intuitively, just to go back to that, so just like the simple version of it, so hold some outcome fixed that has some inefficiency in the current context. You're saying if I throw in stuff that everybody likes less than this anyways, this inefficiency stays the same. Whereas if I introduce a new one that could be the new optimal, then the inefficiency of this fixed alternative might go up, right?
Exactly.
Should I also think of that like monotonicity? Should I think of the inefficiency should only go up as you add more stuff? So it stays the same as you add about stuff?
We're not requiring that.
Okay.
We're not.
Is that going to be true for the eventual?
It's going to be, you need to say a few more words, but yes, what you're thinking intuitively about is going to be satisfied. Okay. Here's the context. It has two alternatives, A0 and A1. I plotted arbitrary utility representations of the preferences here that only say both individuals prefer A0 to A1. Let's assume for contradiction that the inefficiency at A1 is finite. Now let's add some A2. It's the least preferred, and you know, in these ratios that satisfy the preference over the lotteries, by IDA, the inefficiency of A1 should still be I. The inefficiency of A2, therefore, has to be greater than I. This is by Pareto monotonicity. Now, let's remove A1. It is not the optimal. It is not the thing that you care about. It is something suboptimal in between. By IDA, removing it shouldn't make a difference. Which means that the inefficiency of A2 here is still greater than 1. Now I'd like to remind you that the utility scales are completely arbitrary. Our inefficiency notion only depends on the ordinal preferences. So I scale the utilities like this, which means that here again, you know, I actually didn't change the context, only the way that I draw it. The inefficiency of I2 is greater than I of A2. But now take a look at this context and at this context. Up to the change of name from A2 to A1, we see that these are the same contexts, which means that this should have inefficiency equal I. If anyone is nervous about the last step, it is by neutrality, which means invariance to isomorphisms, that we prove follows also from Pareto monotonicity and IDA. So we got that the inefficiency of A2 here should both be I and greater than I at the same time. So one thing we could have done is say, well, that's impossibility. We can have no social inefficiency function satisfying these two and go home. We chose to do something else. We said
isomorphism here is between contexts?
It's between contexts. Okay. It's changing of names of alternatives within contexts.
Okay, and this preferences over lotteries should just be preserved under that name.
Yeah, we renamed A2 to A1. That shouldn't change anything. So what we chose to do instead is to say, well, let's call this inefficiency infinity, which means that here we have inefficiency infinity here and infinity here, even though this should be greater than this because of Pareto monotonicity, but fine, let's squint at it and say if both are infinity, that also satisfies Pareto monotonicity. I should say importantly, this is never an issue when individuals are not indifferent along the entire Pareto frontier. Here both individuals are indifferent across the entire Pareto frontier because the Pareto frontier consists of a single point. Whenever you have a real tension, a real trade-off, there is no individual that is indifferent across the entire Pareto frontier, you will not have this issue. This proof will not tell you that you need infinite inefficiency, and the social inefficiency function that I'm going to define for you later will not dictate infinite inefficiency either. So it's only in this specific case of, kind of degenerate Pareto preferences over the Pareto frontier. I think I'm going to have to skip most of the related literature. There is a lot. It's beautiful. It goes back to the 50s. I'll just say that to our knowledge, our paper is the first that for arbitrary sets of alternatives axiomatically microfounds a social welfare function that depends only on the ordinal VNM preferences over alternatives, whose numeric value rather than induced order is unique and cannot be arbitrarily shifted, and which can be meaningfully compared across contexts. We are also unaware of any paper that uses or characterizes even the order induced by our social welfare function, and more related work. Okay, axioms. So we're going to have 7 axioms that define our social inefficiency function. I know 7 is a lot, but you need to pinpoint something cardinally that requires work. First axiom is Pareto monotonicity. As we said, the classic version would be, let this be a context for every x and y. If x is weakly preferred to y by everyone, then the inefficiency better be weakly smaller. If it is strictly preferred to y by even one person in addition, then the inefficiency better be strictly smaller. And as we said, the first thing, this is too strong. We need to weaken it to allow for infinite inefficiency. So we're going to say either the inefficiency is strictly weaker or they're both infinity. This turns out to be slightly too weak in the sense that strict Pareto monotonicity across many, many papers has the purpose of making sure the function that you're defining is not constant. And as this is defined now, it allows it to be constant infinity. So we're going to slightly strengthen it, still weaker than what's written in white here, to make sure it doesn't allow for that. So we're going to say either inefficiency at x is less than at y, or they're both the same, but there exists another alternative that everyone likes better than x that has finite inefficiency. So we don't allow for infinite inefficiency across maximal chains ordered by Pareto dominance. So this is kind of a right in between axiom, but overall I would like to still emphasize this is still weaker than what we started with. So if you like what we started with, you should like this. Axiom 2, anonymity. If we permute the identity of the players, so we permute the numbers, whoever was individual 1 is now 5, whoever was 5 is now 3, etc., we don't change the inefficiency of any alternative. So far for ordinal aggregation. Let's move on to intra-context cardinal comparability. This is to your question, Tim. We have an axiom we call it expected inefficiency, kind of a nod to expected utility, saying that if you have 2 lotteries and you randomize between them with probability alpha, then the inefficiency of the lottery is the expected inefficiencies at the thing you randomize between. So this is the linearity that you were asking about. There are 2 ways to interpret this. One of them is saying that the social aggregation of inefficiency is risk neutral. So it's saying we don't artificially impose any risk attitudes for society when aggregating over the individuals. The other one is noting that one of our main use cases, that's going to be our application, is quantifying the social inefficiency of the outcome of randomized mechanisms. And this says that the social inefficiency of a randomized outcome is the expected social inefficiency of the realized outcome. So this is our third axiom. Fourth axiom is you cannot not have an Yannai A axiom whenever you axiomatize something. So this is independence of irrelevant alternatives. So usually Yannai A looks like this. You have a context, you take a look at the context C prime with, over a subset of the alternatives. So you drop some stuff and you say if these share some property, have the same indifference point, have the same disagreement point, whoever has seen such papers know what I'm talking about. If they share some property, then for every 2 alternatives, if the inefficiency of one is lower than of the other in one context, it should be lower than the other in the other context as well. So we need to understand what share some property should mean here. We don't have any disagreement point here, unlike bargaining, the bargaining literature. We don't have, this is a direct quote from the paper that defines the Nash social welfare function. We don't have a distinguished alternative which represent one of the worst states for all individuals. For example, we may imagine that all members of society die. We just said we don't want to artificially have to include this kind of writtenness in our model. So we need to do something else here. Fortunately, Al Roth, before he was a matching guy, he was a bargaining guy, and he looked at Yannai A with respect to other reference points, not the disagreement point. In particular, he looked at 2 endogenous points. One of them he called the ideal point. It's an imaginary alternative in which every individual receives as much utility as in her ideal alternative. So formally, two contexts have the same ideal point if each individual is indifferent between their favorite alternative here and their favorite alternative here. And he looked at the point of minimal expectations, which is an imaginary alternative in which each individual receives as much utility as in her least preferred undominated alternative. So again, two contexts have the same point of minimal expectations if for each individual their least preferred undominated alternative here is this, they're indifferent between their least preferred undominated alternative here and their least preferred undominated alternative here.
So are these just sort of saying like X prime includes the right stuff, basically?
No, these are saying
like the ideal point, I feel like you're saying in X prime should be...
If you remove stuff in a way that doesn't change the ideal point or the point of minimal expectations, certain properties should hold. So really what we're saying here is if C and C prime have the same ideal point and same point of minimal expectations, this better hold. This is going to be our axiom. And note that the more points that I put here, the weaker the axiom becomes because there are less pairs C, C prime for which this axiom has bite. So we included everything, all the endogenous points from Roth 77. The last thing...
I am a little confused because the word utility appears in these definitions.
Sorry?
Right? The word utility appears in these Roth definitions.
Yeah,
right?
but as I now phrase it, you don't need the word utility. You can say indifferent between their favorite here and here, or indifferent between their least favorite and dominated here and here.
Right. So like, for example, you pick some player, you say, what's your favorite in X? You would like to see that same alternative appear in X prime.
Or something equivalent to that, if they have several favorites. Yeah. Last thing, I'm going to want to turn this into a cardinal rather than ordinal axiom. So instead of saying, in this case, X is societally preferred to Y in C prime if and only if in C, we're going to say X is societally preferred to Y in C prime, but the same amount that it is societally preferred, X is societally preferred to Y in C prime, but the same amount that it is societally preferred to Y in C. So this is the cardinal version of IA, and just to show you that I'm not cheating in any way, we're going to say whenever neither of the sides is infinite minus infinity, if one of these is infinity minus infinity, the axiom has no bite. So I'm not cheating here with infinities. So this is IIA. Axiom 5, almost there. Independence of irrelevant preferences. So what is this? So axiom 4 was about comparison across two different contexts with the same individuals. This is going to be comparison across contexts with different individuals. So we're going to have a context C and two contexts D and D prime over the same alternatives with the same number of players but different preferences. You can think about M people here and M different people here. And we're going to talk about the composed context C composed D. What does this mean? It means putting the context side by side, thinking about them as a single big context. So the alternative set is going to be X, pure alternative set is going to be X cross Y. So each alternative is a pair of what the first context gets and what the second context gets. There's going to be N plus M alternatives, individuals, so sum of individuals. The first N individuals only care about the marginal over X. The second the last M alternatives only care about the marginals over Y. This is, for whomever knows the definition of von Neumann and Morgenstern of composition of games, this is exactly the same thing, but not for games, for contexts. So we're going to say the following. Take the same one alternative in Y and two alternatives X and X prime in X. And we're going to say in C composed D, if you take a look at the difference in inefficiencies between X, Y, and X prime Y, and in C composed D prime, different alternatives over the Y component, you take a look at the difference between xy and x prime y, these should be the same. What's the idea here? The idea is that we have not changed the y component, so preferences over the y component should not change this difference. We only changed the x component from x to x prime, and the preferences over the x component are the same, so the change in inefficiency should be the same. And again, if one of these sides is infinity minus infinity, this axiom has no bite. So this is about comparison across contexts with the same number of different individuals. N plus m here, n plus m here, but different m. Finally, we have duplication. This is for comparison across contexts with different numbers of alternatives. So let's take a context C, and let's take a look at the k-wise self-composition of C with itself. So we take k independent copies of C, we self-compose them. So we take k copies of C, put them side by side, take a look at them, treat them as a big context. And we take two alternatives, x and x prime, and we say the difference between the inefficiencies of all x here and all x prime here should be the same as the difference between the inefficiencies of x and x prime in the original context. This is an axiom that says we don't want the inefficiencies to blow up artificially just because we're duplicating, or to diminish just because we're duplicating. This is an axiom that says our inefficiency notion should be some sort of a per capita notion. I'm not saying if it's a arithmetic average or geometric average or harmonic average or whatever, but it should be some kind of per capita measurement. This is what this axiom says. This will allow us to compare contexts of different sizes and have meaningful comparison. And again, if one of these is infinity minus infinity, this has no bite. Final axiom is the shortest axiom. It says in every context, there should be some alternative that has zero inefficiency. There should be a best thing in every context, not saying what it is. It should just exist. So these are our 5 axioms. For ordinal aggregation, we have Pareto monotonicity and anonymity. For intra-context cardinal comparability, we have expected inefficiency. For inter-context cardinal comparability, we have IA, IIP, duplication, and feasibility. Characterization, this is our main result. It says there exists a social inefficiency function I hat. I'm going to show you what it is soon enough, such that the following holds. Any social inefficiency function I that satisfies our 7 axioms, or rather any social inefficiency function I satisfies our 7 axioms if and only if it is a constant, finite, positive constant times I hat. So this means that our 7 axioms uniquely characterize a social inefficiency function up to a single multiplicative constant across all contexts at the same time. If you multiply in one context, you should multiply in all contexts. So you can still compare ratios of inefficiencies across different contexts. Let me show you what I hat is. Oh, furthermore, and this is where we pay for having 7 axioms, dropping any of these 7 axioms invalidates this statement. So for each one of these 7 axioms, we have an example of a social inefficiency function that satisfies the other 6, but does not satisfy this theorem. So none of our axioms is redundant. They're logically independent for people who like...
For that axiom where you needed to have both of the Roth notions, can you prove you need both? Remember the...
If you put only one, it strengthens the axiom.
Context.
If you have only one there, it strengthens the axiom. So that
There's
is...
an or is an and in that axiom?
It's an and. If C and C prime have the same ideal point and the same point of minimal expectations,
so only then
this axiom says something. Okay. Yeah, so we threw in all of the endogenous, points from the bargaining literature into that axiom to make it as weak as we know. So here's our construction for I hat. So let C be any context and pick some utility representations, we're going to see that the calculation that follows does not depend on this choice. Denote by FC the Pareto frontier of C. So this is the, let for each I, for each individual I, let UI max be their maximum utility across the Pareto frontier, UI min be their minimum utility across the Pareto frontier. And now we're going to define what is this. This is the per capita, meaning average, sum of normalized utilities, normalized so that each utility number is normalized to have minimum 0 and maximum 1 along the Pareto frontier. So we normalize each utility function to have minimum 0, maximum 1 along the Pareto frontier, and then this is a social welfare function that is utilitarian. It averages the utilities at the alternative that we're talking about. And then we define our inefficiency as looking at this thing, finding its maximum, let's call that 0, and then our inefficiency is loss in this measure compared to optimum. Let's do an illustration. So here's the context with some utility representation. We start by finding the maximum and minimum for each individual across the Pareto frontier. This is one's favorite point. This is one's least favorite point on the Pareto frontier. This is 2's favorite point. This is 2's least favorite point along the Pareto frontier. So now this is the normalized unit of one's utility function. This is the normalized unit of 2's utility function, and we average them. So this is 1, 0, this is 0, 1, so each of them has average half. This is v equals 0, this is v equals 1. And which means that this is the unit of v. This is the maximum of v across all alternatives in the context. So we call this I hat equals 0. And then we count back from 0 in the units of v. So if this was the unit of v, this is the unit of I hat, and this is the line of I hat equals 1. This is inefficiency 1. This is inefficiency a bit more than 1. These are between 0 and 1. This is the only social inefficiency function, again, up to this constant. You could normalize this to be a half unit and this to be a half unit. This, this would mean multiplying everything by 1/2, but that's the only degree of freedom you have, and you need to normalize in the same way across all individuals, across all contexts. So this is the only thing that satisfies our 7 axioms. Going one last time back to Arrow. So Arrow says, as it stands, the sum of individual utilities seems to be excluded by the entire nature of the present approach, since we agreed to reject the idea of cardinal utility and especially of interpersonally comparable utility. However, presumably the sum utilities could be reformulated in a way which depends only on the individual orderings and not the utility indicators. The only way I can see of making the sum of utilities depend only on the indifference loci, meaning the equivalence classes of utility functions, is the following. Since to each individual ordering there corresponds an infinite number of utility indicators, set up an arbitrary rule that assigns to each indifference map one of its utility indicators. Arbitrarily choose consistently for every preferences always the same utility function. Then the sum of particular utility indicators chosen by the rule is a function of the individual orderings and can be used to establish a social ordering. So to some extent this is what we do, except that the thing that we have that for each preference order chooses a specific utility representation is not an arbitrary rule. It is the unique rule that follows from our axioms. I think we can skip.
Can you go back to the construction of just the definition of the function? So you just so when you have a degenerate Pareto frontier.
So when we have a degenerate you define by 0, that's exactly when you get the infinities we talked about. So you get, this is what we have in this slide. So we can say that an individual I is frontier indifferent if they're frontier along the entire Pareto frontier, these are exactly the individuals for which you divide by 0. And you get infinite inefficiency if and only if this point is strictly less preferred than the Pareto frontier by a frontier indifferent individual. This is if and only if. So along the Pareto frontier, you always have finite inefficiency, but for for alternatives that are strictly preferred less than the Pareto frontier by a frontier indifferent individual, you get infinite inefficiency. That's the only case.
I see, but so if you have a full Pareto frontier, you said this earlier, then everything's finite.
Yeah.
Okay.
So if no one is indifferent across the Pareto frontier, which is usually the case because we model trade-offs, we don't model, then everything's fine. Okay, application. So for our application, we go to a setting where we have no transfers, no outside options. Not only there are no monetary transfers, but it's repugnant to compare or measure using money. If you go to to City Hall and you tell them, I want to allocate students based on how much they would have been willing to pay to get to that school if you would have charged them, they would, throw you out very, very quickly. So it's a context in which it's repugnant to even measure using money, which means that the interpersonal comparison is very challenging. Meaningful, precise cardinal values for utilities are very challenging to justify. And we're going to talk about a setting with no outside options, as I said. So we're going to have n individuals, n objects. Each person must get an object. There is no option of staying without an object, meaning that you cannot say we're normalized so that being without an object is utility 0 or anything like that. And this is going to be our context. So I think we can skip these, but we're going to say an ordinal mechanism is a mapping from profiles of strict rankings over the n objects to distributions to randomized matchings. So an ordinal mechanism is something that gets orders over objects and outputs a randomized matching. We assume, I skipped that in the previous slide, we assume everyone has strict rankings over objects. An ordinal mechanism is truthful if truthfully ranking the objects is dominant in the induced game. And for a truthful mechanism mu, we're going to denote by this the outcome at the truthful ranking equilibrium. Random serial dictatorship is the truthful ordinal mechanism that's used abundantly for assigning housing units by governments, by colleges, internships, school slots, whatnot. And it works very simply in uniformly random order over individuals. It matches each individual to the not yet matched object ranked highest on her report ranking. So, we draw an order. First is Tim. Tim picks his favorite. Then his favorite is gone. Next is Yuval. He picks his favorite among those that Tim has not yet taken, etc. And I don't only say that it's used abundantly in other places. This is also how we assigned offices in the new economics building at Harvard. You see that these are the people who already picked, and now it's Matthew's turn to pick his office among the remaining ones. By the way, we're thrilled to have Leah Nagel join us in the fall. Theorem. There does not exist any truthful ordinal mechanism whose worst case inefficiency over all matching contexts is better than about 72% of the worst case inefficiency of random serial dictatorship, taken worst case over all matching contexts. So I should note that saying worst case inefficiency across all contexts is meaningful only because we have inter-context comparability for I hat. And saying this, comparing this with 72% of this is only meaningful due to the cardinal nature of I hat. A corollary is that for every social inefficiency function that satisfies our 7 axioms, there is no truthful ordinal mechanism that shaves more than 28% off the worst case guarantee of random serial dictatorship. And this should be compared to a well-known ex ante inefficiency result for random serial dictatorship. So we're kind of showing here, well, we know it's ex-ante inefficient, but it's actually ex-ante approximately efficient, which kind of, explains why it doesn't perform very poorly. And the proof, this was the easy part for us. We adapt proofs from this wonderful paper that bounds the price of anarchy of random serial dictatorship. So they take a look at the asymptotic order of magnitude of the ratio between the optimal and realized sum of utilities as the number of objects go large. We take a look at the difference. We don't do asymptotics, but the hard parts of the proof are really, the most naive translation you can think about from their paper. So we think about this as also a proof of concept that price of anarchy results can be translated with not a lot of effort into results about our social inefficiency function. They do this with the assumption that utility functions are exogenously normalized to 0, 1. We make no assumptions about exogenous normalization. So what did we have here? We had a cardinal social inefficiency function. Its numeric values, not only the order, are uniquely defined. We demonstrate the applicability of the axiomatic approach for micro-founding economically meaningful quantitative comparisons of efficiency. Maybe there are other axioms to do this, better axioms. I would love to see follow-ups on that. Our utility is in units of the diameter of the utility function's range over the Pareto frontier. For frontier indifferent individuals, those that we talked about, we satisfy the axioms using a degree of freedom that we don't usually get in the social choice literature, but we do get with the cardinal approach, which is kind of saying these two are so bad that we're going to squint at them and say they're the same, they're both infinity, rather than saying, which is better, which is worse. Inefficiency bounding theorems allow us for gradual progress over papers. We didn't try to improve this 1/2 ln 2. It's what came when we translated in kind of a naive way the proof from the price of anarchy of RSD paper. Maybe this could be improved. What about other applications? What about bargaining? Instead of disagreement point, we have kind of an agreement region. Management science textbooks talk about framing bargaining with respect to a zone of possible agreement. Maybe there's something there, I don't know. And what about microfundation for other approximation theorems? Something like some quantity is at least a specific fraction of some other reference quantity. What about fairness, approximate fairness? Axiomatize quantitative fairness, inequity, cardinal comparative statics. Instead of saying when this goes down, this goes up, say when this goes down, this goes up by a certain function of what happened here. So these are all exciting future directions, and I'll stop here and thank you all.
Just a very basic kind of sense check. So if I take a context and I rescale the VNM utilities of the players by an affine transformation, the C that you would obtain would be distinct across just fixing the set of alternatives, the set of lotteries. But what is, if as I rescale VNM index?
Okay, so you rescale these, then the I hat that I calculate is going to be exactly the same. Why? Because
Can I
I'm
suggest
going
you
to
put the formula back up on the...
Yeah, I'm going to put the formula back up.
I see, because it's the max versus the min, and in the
Yeah, exactly. So that I'm going to renormalize.
Yeah.
I'm going to normalize between 0 and 1, regardless of how you scaled. I'm going to renormalize to the same thing. The C only comes in, if you normalize so that this is half a unit and this is half a unit, and in all contexts you normalize so that this is half a unit and this is half a unit, you also get something that satisfies our 7 axioms, which is exactly 2 times, it's exactly half of our I hat. So the only degree of freedom you have is to what is the size of the thing you normalize to here and here, but you need to normalize to the same amount across all individuals, across all contexts. So it's only a multiplicative factor. And as we saw in the application here, so you take any I, so you could multiply by 13 here and by 13 here, but it cancels out because it's a positive finite constant.
if you look, maybe a couple of related questions. So like you could ask about having a function for a restricted class of contexts, where maybe you'd have more than just this unique one, perhaps.
Yeah.
And then relatedly would be like if you go to your motivating examples at the beginning, like the selfish routing games and kind of welfare maximizing mechanisms.
So,
like you don't recover those functions.
No, I don't
from
recover
this, right?
those,
Yeah.
but those are settings in which you have extra information
Right.
that our contexts don't have.
Right.
So I'm not by any way saying don't use extra information if you have it, but sometimes you don't have it.
Right. So what I'm saying is there may be like this rich intermediate region where I'm thinking of it as like a restriction on the context, if you like additional structure on the context, where you maybe could then characterize the family of reasonable sort of functions
Maybe.
to think about.
Maybe.
So, okay.
Maybe, yeah. This is for all contexts, and we use in our proof the ability to jump between contexts and stuff like that. So yeah, if you restrict, certainly you can get more. Would be interesting to see what you get there. But again, I'm not saying. So you could. I think that doing price of anarchy for driving time is great. I think you might want to do it with scaling so that 0 is instantaneous arrival, like in your papers. Someone else might want to do it so that 0 is arrival as if the roads are empty. That's a different 0, gives a different thing. So different applications have different extra information that they give you about what are reasonable points to ground yourself. This is a study about what if you have none of that, showing that you can still do something.
So for this 2 log 2, does that have any interpretation beyond if I proved the theorem for a smaller number that I have a tighter bound, or is there some way?
Say it again?
So for the 2 log 2 in this theorem,
Yeah.
does it have any interpretation beyond if I proved the same theorem with like a smaller constant there, that's a tighter bound, or is there an explicit interpretation of what 2 log 2 means?
No,
here?
2 log 2 is what we got when we plugged in the proof from the price of anarchy of our SD paper. But we think 70% is a pretty good approximation. But I don't have any reason to think this is tight.
Or I guess is there a interpretation of what 70% means here? With the...
I don't have one.
Okay.
If you have one, I'd love to know.
To be specific here, if we are able to show 1 by log 2, it is like literally a twice improvement. That's the entire point that we are trying to make here.
If you can show 1 over
Log 2, for instance. Or 1
no,
by 4
1 over
log
log 2 is more than 1.
Sorry, okay.
You will
If
not
we
be
do
able to
1 by
shoot
4,
that.
okay, that's tighter. Okay.
If you can prove 80% instead of if you can prove if you can prove 86%, for example, would that be it will close half of the it will, instead of bounding by this, it will somehow cut by half the distance between it will cut by half the thing you can shave off. So this says some other mechanisms might be able to shave off 28% of the worst case guarantee of the worst case inefficiency. If you prove 86%, it means that you show that no other mechanism can shave off more than 14% of the worst case. So it will be a sense of a 2 times improvement. Yeah. Thank you so much.